Okay, so let's start this session. Let's come back to the procedure of finding the MLE. Uh, in previous case, we demonstrate a case where uh, we have trouble finding it. We have trouble finding it by following standard procedure. Then we find the asymptotic one, and the asymptotic one comes from linearization, a linearization approximation for the Taylor expansion, right? It actually comes from the Taylor expansion. And then we will be able to calculate its asymptotic mean and asymptotic variance, and it approaches the true value in CILB, which is good. So now let's take a look. Is there a way or better approach of finding the MLE? So the MLE for a scalar parameter is defined as the value of theta. Now we are formally defining it. The MLE for a scalar parameter is defined to be the value of theta that maximizes px theta for x fixed. How come for x fixed? Because as we mentioned, while you are doing estimation, you take measurements, but when measurements is given, it's considered constants, right? It's considered constants. As a result, your PDF becomes a function of parameter instead of of course it's part of the data, but data is no longer random variable. Data is constants after measurements. This is called posteriori, right? Posteriori. So uh, for x fixed, then the value of theta that maximizes the x likelihood function, the maximization is performed over the allowable range of theta. So in the previous example, this was a larger than 0. And since uh, p of x theta is will also be a function of x, the maximization produces a theta head that is a function of x. The rationale for MLE hinges on the observation that p of x theta dx gives the probability of observing x in a small volume for a given x. Okay. Okay. So we want to find a, a theta value, the theta value that maximizes p of x theta, maximizes p of x theta, and then the idea is, let's take a look at this. This is p of x. X is being observed, so let's think of it as given, and then it has value theta. It's a function of theta, so it's a function uh, observed over the range, the range, not the range, the domain of theta, the domain of theta, and then we like to find a theta 2 that maximizes this function. Then that we will think of it as what? We will think of it as uh, we will think of it uh, as the maximum likelihood estimator for theta. Okay, so that's the idea. Okay, so DC level in white Gaussian noise. To actually find the MLE for this problem, we first write a PDF as this. PDF as this. Notice that the A is in the variance, right? A is in the variance. It's not just at the DC level, it's also in the variance. Okay, so consider this as a function of A. It becomes a likelihood function. Differentiating the log likelihood function you do differentiation, you get this. And then, as you know, we want to find the maximum value of a function. We usually do differentiation, first order differentiation. The thing is, uh, it may involve some calculus, so do it carefully, and then we get this function and set it to 0, and then it produces this. Set it to 0, then we get uh, this whole thing equal to 0. Of course, we have done some simplification because it has x and a, so you have to simplify it a bit and setting it to 0. You get something like this, something like this. And then solving for a hat, it produces two solutions. Uh, so solving for a hat, we get a hat equal to this, a hat equal to this. 这是一个 a hat 的多项式二次式，所以还记得那个公式吗？它当它等于0的时候，有一个2a 分之负 b 正负根号 b 平方加 ab 的那个公式，所以你用那个公式，你就可以得到这一个，就是一个多项式二次式等于0的公式。It has positive negative terms. Then of course we choose the positive term because we know a larger than 0 a priori, right? A priori. So we now get this estimated. So we take a look at this. At the beginning, we say we are given a, a function of data, and then we don't know about it. We don't know what happens. Right? We don't know what happens for this a hat. We don't know how it come from. Now it seems like we have a better way of seeing it, right? We see it as a function of this, and then we want to find an extrema. We take the derivative, and then we get this. Now you see that is to be identical to this, right? So now you have a procedure of getting it. Okay. So the other thing is DC level in white Gaussian noise. For the received data xn equal to a plus w, where a is the unknown level to be estimated and wn is wgn with known variance sigma squared. The PDF is something like this. Then taking the derivative of the, notice that you have sigma squared here. If you see this, you have a as a variance. Now you have sigma as a variance. So you take the derivative of the log likelihood function with respect to a. Then of course it's easier because this sigma square, when it's taken with respect to a, it will be 0. This part will be 0. And what remains is this part. So you set it equal to 0, set this equal to 0. You get MLE equal to that. So that's a trivial simple case for DC level. But we already know that, right? We already know it. And even for this class, I think you have practiced it many times, even before you learn this class for this estimator. So you now know that this is not only a trivial solution, it's a MLE, and it's the best one because it achieves CILB. So you know more than just a simple sample mean, right? You're supposed to know more than that. Okay, so now we turn to the properties of MLE. We know MLE. So uh, so we now know MLE is asymptotically unbiased, achieve the CILB, and has a Gaussian PDF. So in fact, those things are all properties. That's what all we want, all we like about estimator. That's why a lot of uh, applications actually adopt MLE for the estimator. If we recall a little bit, we talk about trivial estimators, linear estimators, BLUE estimators. Now we come to MLE, and it seems like MLE is more complicated. It's more complicated in terms of formulation, in terms of the procedure of getting MLE is more complicated, but it has these nice properties. So its distribution will be theta hat distributed by n theta, then feature information matrix minus 1. And feature information matrix we have introduced it in previous chapters, right? It's a partial derivative of likelihood function with respect to the parameters in the elements. So it's asymptotically distributed according to this. Okay, so this result is quite general and forms the basis for claiming optimality of MLE. So there is no wonder why so many people, so many applications adopt MLE. Then of course in practice it is seldom known in advance how large N must be in order to hold this, right? This is like when you take samples, then how much is sufficient? How much is enough, right? Similar things happens in, for example, machine learning. How many samples are enough, are sufficient for training a machine, training a AI machine, or training a machine learning model? How much is enough? There is no concrete answer for that, but typically, if it depends on the data model. If you can, you try to take as much as you can. If your system allows you to collect data, you try to collect more as much as you can, particularly for modern circuits, modern DSP systems. We actually take a lot of samples, like millions, billions of samples, even in a couple of seconds. Okay, so uh, it's a nice property. So now we introduce it and up to here. And I think that's all for today. And we have uh, sufficient time to continue this uh, course. So 先前我们是大概就是多上一些进度跟时数啊，所以进度也比较快。那我想在这个时候，我们今天就上到这边。那我们是礼拜三会从这边继续下去。谢谢各位。